So, hello everyone, my name is Mert Koşan. I am a PhD candidate in UC Santa Barbara in Computer Science Department. Today I will present our work, Global Counterfactual Explainer for Graph Neural Networks. And this work is done in collaboration with Zishi Huang, Sora Media, Sayan Ronu, and Ambu Singh. I also want to thank SIG-IR and NSF for funding my travel expenses. Deep learning achieves best performances in various application domains. And explaining deep learning decisions is a critical problem, especially in high-stake application sectors, healthcare, finance, or law enforcement. There are multiple recent articles discussing that explainability and transparency should be the main core of your AI application. This will build trust between human and AI. An ethical problem using AI systems will not be an issue. Another article from Nature claims that some scientists are already using chatbots such as ChatGPT as their research assistants. However, quality and correctness of these chatbots are questionable. Therefore, we need to explain these deep black box models. Our goal of this work is to present post-hoc explainer for those deep black box models. So here we have an AI decision system that synthesizes a mortgage application, and this particular application is denied by the system. Now we need to understand the reasons. One way is to check which features are important. For example, here, depth parameter can be important, the customer should focus on. Better way of explanation is to provide recourse in terms of local counterfactual. Counterfactual means another instance, ideally with minimal changes to the input class. For example, if we change depth parameter from medium to low, the application will be approved. On the other hand, global counterfactual idea tries to define a general rule, and it will make it easier to explain compared to local counterfactual one. For example, here, the rule is if credit score is medium and stable job year is 2, then depth should be less than or equal to get approved. As in graph explanations, the idea is similar. We have graph neural networks decides formaldehyde molecule is mutagenic molecule, in other words, an undesired molecule. Now we need to understand the reasons. One way is to check which subgraph is actually relevant to this prediction. Here we can have carbon-hydrogen bond is the reason. Another way, similar to the mortgage application example, we can find a local counterfactual of formaldehyde molecule. If we remove hydrogen bond and add hydroxyl bond, then we will have a local counterfactual, formic acid, which is non-mutagenic molecule. However, subgraph importance and local counterfactual methods are unlikely to show a bigger picture. Global counterfactual, again, tries to define a general rule which makes it easier to explain. For instance, here we can say, instead of providing formic acid as a counterfactual example to formaldehyde, we can say, given any molecule with carbonyl group, this CO, it needs to have hydroxyl bond to be non-mutagenic. And our work is the first one exploring global counterfactuals in graph domain. Our goal is to find general recourse rule, counterfactually and globally explain the prediction made by GNNs. Specifically, for any undesired graph G, R of G should be desired. In binary classification context, let class 0 is undesired class. If GNN of G is 0, GNN of R of G should be 1. We want to make this R function not complex function because we want to make it explainable. To satisfy these two conditions, we let global recourse R function as counterfactual summary graph set C, and all graphs in this set will be desired. With this definition, our R will be recourse rule because for any undesired graph, we can find counterfactuals as the closest graph in our set C. We can use some distance metrics such as graph edit distance. In this particular example, we have counterfactuals C1 and C2, and undesired graph G1. And the distance from C1 G1 is 5, and C2 G1 is 10. So the counterfactual of G1 will be selected as C1 because it has fewer edits. And this will make our R function easy to explain. So now we need to quantify the quality of this summary set C. Our first criterion is cost, where we try to minimize recourse cost for all undesired graphs. Cost is important because we want to have similar graphs as counterfactuals to undesired graphs. In this particular example, since we will select the closest counterfactuals, C1 will be selected to G1, and C2 will be selected to G2 and G3. And the cost of this set will be 5 plus 3 plus 15 as the number of edits in the paths. The second criterion is coverage. Given edit budget data, it will be impossible to cover all undesired graphs. Our aim is to maximize the coverage for representing all undesired graphs by our summary set. In this particular example, G1 and G2, and since we are setting our theta equals to 5, G1 and G2 will have potential candidates, counterfactual candidates from our set. However, G3 will not be covered. So the coverage value will be 2 by 3. The third and the last criterion is interpretability, where we try to make our set C as small as possible to make easily analyzed. Based on this criteria, we formulate our problem as maximizing coverage of set C such that size of C will be given budget K. And in the paper, we show that this problem is NP-hard by reducing from maximum coverage problem. Now I will introduce our heuristic method to solve this problem. To generate counterfactual summary set C, first we need to search counterfactual candidate S. To efficiently organize the search space, we leverage graph edit map, which represented as neighbor graphs with one edit. For example, the edits can include node edge removal, node edge addition, or node label change. With this way, we will have the most similar graphs as counterfactuals to undesired graphs. To efficiently search the space, we propose to use vertex reinforced random walk, which considers the number of visited information and importance of each visited graphs. And in the literature, it has been shown that this method converts the representative set, which is useful for us because we also want small representative counterfactuals that covers all undesired graphs. Importance function in this formulation is very critical and problem specific. We use GNN probability to explore only counterfactuals. We also use coverage and gain, which represent how many additional number of undesired graph will be covered by this new candidate. Since we cannot explore all graphs in the universe, we start with random undesired graph in our data set, and we explore the neighborhoods with a teleportation back, some probability of teleportation back to another undesired graph. With this way, we will explore the neighborhood of all undesired graphs, and it will end up having a representative set by using number of visited information. After we find counterfactual candidate set S, we apply a simple greedy algorithm to find size K subset of them as our final counterfactual summary. In our experiments, we use 4 well-known graph classification datasets. Since we are the first global counterfactual explainer in graph domain, we compare our methods with 2 state-of-the-art local counterfactuals, and ground truth counterfactuals are actually the opposite class, the graphs from opposite class in the same dataset. And the table shows our method outperforms the baselines with size of C equals to 10. So the below figure shows the coverage and the cost performance with size of C varies from 1 to 100. And our method consistently outperforms the competing baselines under all different sizes of C. To show the usefulness of our method, we also conduct case study. We have 4 input undesired graph from 8 datasets, and these molecules are inactive against AIDS. So the counterfactual of them will be active against AIDS. So we generate local counterfactuals using our baselines, and the baselines are actually removing 1 or 2 edges from the original graphs, which makes it hard to generalize. On the other hand, our global counterfactual is defining a general recourse rule. And indeed, while the input graphs have ketone or ester structure, our global counterfactual will have aldehyde structure. In the literature, it has been shown that the molecules with aldehyde structure are useful combating HIV. This also demonstrates the usefulness of our methods in real-world graph applications such as drug discovery. As a summary of our contributions, we formulate a new problem of global counterfactual reasoning of GNNs in graph classification. We show that the problem is NP-hard, and we present the first global counterfactual explainer in graph domain. And we also demonstrate the effectiveness and usefulness of our methods via experiments. We hope our work can help researchers in exploration of explaining deep learning and graph models. Thank you.